Greetings, welcome. So I want to finish this up. The last time I thought I was recording when I wasn't recording, and vice versa. So hopefully this time I'll get it right, and hopefully we can do it rather quickly. And so the idea, as I've been talking about for a little while here, is here we have some 22 gauge wire. We'll run the thing. I'm going to pick a spot. You know, the behavior changes, whether it's there. We're just going to pick a spot. And then we're going to flip that out for 26 gauge. And as we talked about, there's an odd thing with the definition of ampere turns and resistance and amp turns. And that is that if you have the wire diameter, the resistance would become 1/4 because the cross-sectional area would be 1/4 of the wire. But you should be able to fit, you know, I mean, there's things with, well, the insulation or how well they're going to fit in. You should be able to fit close to 4 times as many wines. So if we say you could fit 4 times as many wines and your amp draw is now 1/4, then you would have the exact same number of amp turns, but you would be drawing 1/4 of your amperage. So I thought that was kind of interesting. I mean, everyone is sort of, I think people more commonly think that, well, if you have a lot of thin wire on here, it detects a changing magnetic field much more sensitively than if you have a few lines of thicker wire. And that's true, but the converse or obverse or whatever you want to call it, that perhaps you get more motive force out with the thinner wire for a given input of energy is a little bit different. And we've also kind of discussed why this setup kind of sucks, and that's because you have that ferrite core. That ferrite core is really very good. So I mean, in terms of magnetic, not magnetic permeability. I'm blanking on the term, but the idea is that this is a good core, better than welding rods or something like that. So it's possible your total magnetic field is, 80% or more from the core. So then the next question is, well, you dummy, why don't you just remove the core and do it with air cores? And that would give you a clean experiment looking at the ampere turns, as opposed to, the ampere turns, if I don't have this backwards, comprise the H field. The B field is the ampere turns from your wines plus the environment, which the environment is significant there because you have that. Whereas if you have an air core, it's essentially just the H field, the ampere turns. You can see they're super glued in there. They ain't coming out. I'd have to, there's no way in heck they would come out. So at some point before too long, I'm sure I'm going to be winding things that are air cores, and then we'll look at that with different wire gauges. But you should still be able to see something here, and I have seen it. And so I want to try to repeat it like a third time, and hopefully this time it doesn't like blow up and it's the exact opposite. So let's get moving. What do we got? We got power going through. It's the first thing. Okay, the second thing, I'm giving this a little spin, and we see it's being triggered by the Hall effect. Now, if you were looking for, let's get the rest of efficiency and all that, you would want to look for the place where you can get the shortest pulse there. And then the other thing, if this is not working, is that's 1 switch out of 4. But we're going to say that they will all work. Okay, so first, we're still just at 1.9 volts there. Yeah, we see we got it spinning. So that's good. Now, next part. Okay, the next part is this thing is, you're getting both the collapse of the magnetic field as well as something from the magnet spinning past. That's going through a bridge rectifier out to here. We're measuring that, and we have two 10K ohms in parallel, so 5 k ohm of resistance, and we just want to see that something's coming out there. We're not worrying about like how good is the spike, how good is, we're not worrying about this. This is being put in there now, and I'm going to shut it off. Basically, why we have it in there now is just to, and granted, at 2 volts it doesn't make a difference, but we just want to protect that if you don't give this a place to go, then it rattles around back to here and here and here and here, and you fry your switches. So that's basically just to protect things. You could do something with it, like hook it up to a battery, but we're not worried about the efficiency on that. We're just worried about motive power. Now the next part is you can have situations where this thing is freewheeling at, say, 500 RPMs in a particular position. You put a generator or a pickup coil in and you load it so that this is doing work, and it goes down, what did we say, like 500, it goes down to 300 RPMs. And then you can have this thing in another situation, in a different position, where it's freewheeling slower, like 450, but when it's loaded, it's spinning at, say, 400. So in other words, the torque varies and is not necessarily commensurate with your maximum freewheeling speed. So, we just need to pick a spot, and then we need to load it, because I really don't give a flying hoot what this is doing freewheeling. I want to know what it's doing under load. Okay, so I've just thrown a pickup coil in there. It's not loaded yet, but at that 1.9 volts, we're getting like 4.47 volts out, and we're going to load it across a 1k ohm, so that should slow it down pretty significantly with a decent load. And that's what it's doing. It's slowing down now. But again, we're not terribly interested in tracking the efficiency there. We're just trying to get at the idea of motive power and different wire gauge. So we don't even need to keep track of that. We just need to know it's hooked up in the identical same spot whenever we do it across a 1k ohm resistor. Now what's the next thing? So the next thing is we want to run it through here, and this gives us an idea of the milliamps that we're drawing. Now what's the next thing? The next thing is I'm going to fiddle around for a halfway decent spot here. Now, as I said, the behavior changes a lot on all kinds of different variables, this, that, and the other, depending on where it is here, where it is there, what the air gap is, this, that, and the other. I'm gonna find a decent spot, and we're gonna put it there, and I'll put a second piece of tape down there so that we know when we put in a different gauge wire that we're in the exact same place. And then we need to pick a voltage. I don't know, maybe 2 or 3 volts I guess would be fine, because it's spinning pretty quick. So let me just fiddle. I'm gonna diddle around a little with this, and then we'll put in the other wire. You know what, I didn't even diddle around there. It's like this is spinning fine. We are at 2 volts, 15.3, 15.2, 15.3. We're spinning at 375.7 RPMs. I think that's fine for our baseline. So we have that all jotted down now. We're at 2 volts, we're drawing 15.3 milliamps for that many milliwatts, and we're spinning at 376 RPMs. So if we take this 22 gauge out, put a 26 gauge in there, what's it going to do? And hopefully it doesn't do, this worked. This worked previously. It worked 2 times. So hopefully it doesn't like blow up on me now on this one, because hopefully I'll be able to show it to you again, and there's not like some other variable coming into play. But let's flip this out. Instead of the 22 gauge, let's put in the 26 gauge. And I, of course, bumped the Hall effect sensor, the pedal still there for the Hall effect sensor. When I was putting in the different wires, they got another screw up. I gotta fix that. I mean, not fix it, but I need to improve it. It's like too darn big. I can do better with Hall effect going forward. But it seems to be like settling down now. So here's what we're seeing, just running it again at 2 volts. we're at 2 volts, 3.4 milliamps, and 177 RPMs. So now we're at 2 volts, 3.4 milliamps, 6.8 milliwatts as opposed to 30.6. We're doing 177 RPMs versus 376. So a little bit less than half, or that much less milliwatts. So on the one hand, you say, wow, that's great. On the other hand, it doesn't really tell you anything, does it? Because we don't know if we went back to the 22 gauge and slowed down to 177 RPMs, I mean, maybe it would be drawing 2 milliwatts. I mean, we don't know. So what we want to do now, and this is the part where it's worked previously for me, not like super dramatic, but enough to show, we want to turn this fucker up until it's spinning at 376 RPMs, and then we want to see what kind of milliwatts we're drawing. So that's what I'm going to work on now. All right, this is a little bit what I was scared of. We're between 4.3 and 4.4, so we'll call it 4.35. We're between 6.7 and 6.7 and 6.8. That's where it mainly was before. I've been calling it 6.75. I'm going to continue to call it 6.75. And we're spinning at 375. Come on. 375.7 as opposed to 376. So this kind of sucks because, I mean, it's essentially a 375.5, 376, 376, that many milliwatts and that many milliwatts with the narrower gauge. Now, previously when I was doing it, I was getting like a 10 or 20% improvement. And now it's like a 3% improvement. So again, so much goes back to, I bet you if I had it further out, further away from the core, there would be a little bit more dramatic difference. I don't care. I'm getting bored with this. Just kidding. It's exciting as hell. I'm getting bored as hell with this. Freaking. So I'll tell you, we got to do one more experiment, and then I'm going to go on to the stuff that I'm interested in. And depending on if I run into a lot of problems with the third experiment, I'm going to skip it. But the third experiment is, instead of changing the wire gauge, we're going to take a 24 gauge, and I'm going to have to wind a second one of those. And I'm going to put in the air core and glue it in because I don't have any other without air cores. And then we're going to put, one here and one there. Does that behave the same as changing the wire gauge? Or does it behave differently? Normally I got a better improvement. The really interesting thing was with the narrow wire gauge, maybe I showed this in a different video, the spike is much better, which surprised me because everything's going towards the narrow wire gauge, whereas like all the luminaries, like Bedini, he's got that big honking, big as your thumb, what do you call it when you wrap Litz wire. But to stop rambling here, I want to get the second one, the series coil, out of the way. And unless I see something spectacular with that, I'm kind of getting bored with this, and I want to go to like the exotic setups. And so one of those will be a magnetic ramp where you will have, a magnet there, magnet there, magnet there, magnet there, magnet there. And if you have an iron core, it's gonna, if it's out like that, it's gonna boom, pull it in there, and then you blink it and make it spin. That's one of them. Now the other ones, let's take this off just to make it easier to show, and let's put in a different gauge wire. So here I'm just spinning up some 24 gauge at 4 volts, and I just want to show one thing to you. And I guess the way I'd say this is that I still haven't read any more past the first 20 pages of that, like 280 page recent translation of the Andre Ampere stuff. But from the first 20, 30 pages, I sort of got, one of his landmark experiments was, his colleague Volta, Alexandre Volta, had come up with the battery of cells. And this gave people a way to have a consistent amount of voltage as opposed to, like what Franklin was dealing with capacitors or what are they? Leyden jars or whatnot. And what Ampere did was he took the current, put it through a wire from one battery to another, and put a compass magnet needle underneath it. And the compass magnet needle went like that. And that pissed everyone off. Because the wire's going like that, so you would think it would go like that or it would go like that. The force was orthogonal. The force was sideways to it. And as I thought about that, just trying to get to sleep or whatnot, the window motor is that same experiment on steroids. It's the exact same thing as Joseph Newmann's big Eureka machine. In fact, I think Joseph Newmann did it first, but before them all, Andre Ampere did it. The zero force motor is the exact same thing. It's just you're extending out more there instead of extending out more there. And so I'll just show you one more thing here, and then I'll tell you how we're going to do that, because it'll be both simple sorry, but it should be both simple as well as more efficient. So here we have this, and now that I understand Andre Ampere, I have no idea why this spins, but I'll show you what Andre Ampere came up with. So now you can see we've got the coil sitting the wrong way, but the thing's still spinning, and in fact it spins just as well with just as much torque and the same timing and everything else as before. And this is Andre Ampere's, kind of landmark experiment, and you can already see like some things. Obviously, you don't want this as like a circle. You want those as like straight lines right up against there, so that you have the most orthogonal force going on. So I mean, there's, that could be changed, and just to kind of drive that home, it's like, well, what if you do it like this? And what you find is there's nowhere you can put it now where it does anything. So it's like, I thought you just said it was all Andre Ampere. So, wait a minute. No, you can't get it to spin, even with it pumping all that through. And so it's like, why does it spin like crap when those are like that, but it spins like a bat out of hell when you turn it the other way? And the answer is, it wants to spin, but it wants to spin that way, which would mean it would have to start doing that. And it can't do that when this is set up that way. So we go back to how we had it again with Andre Ampere, and instead of a magnetic compass needle, now you just have a magnet facing down, and you find a spot, and it'll spin as well as how it was before. Now I don't understand why it spins the other way before, because you got some of the lines going that way, some of the lines going that way. You'd think they'd cancel out. So trust me when I say I have no idea what I'm doing. But I'm having a lot of fun. Look at that thing go. Ooh. So I'd say along with the magnetic ramp motor, what I'm really looking forward to build, and I think it would be an easier build than trying to arrange, like 15 coils around like that, and it's like, oh, each one gives a 10% improvement or something like that. But what you do is, say you have some square magnets like this, and they're running up there like that. Now you put wire right next to them. Now you have a window motor. So what do you normally do with a window motor? You go zoom all the way around to the other side in the background like there. But that's kind of a waste of wire when you think about it, because what if you took the wire up like that, boom, down like that for the next coil, boom, up like that for the next coil, boom, down like that for the next coil, i.e. a serpentine coil. You now have a more efficient use of your wire. When you just have wire hanging out there doing nothing, then that's just adding resistance without being helpful. So in other words, let's do a serpentine window motor. And then after that, we can think about revisiting the zero force. But I think the very first thing will be the magnetic ramp, and then the serpentine window motor. Before we do that, I got to put in a second coil just to get that done. And I'll probably make a video out of it, unless it's just boring as heck. I mean, unless it's like so exciting I don't bother to share it. Probably won't be the case. All right, so keep smiling, everyone. Thanks for coming along. Bye-bye.